So there's several different ways we find limits. We can find them from graphs, we can find them using tables, and next time we're going to talk about finding them without either of those, but just looking at a function and trying to figure out what the limit is. But again, it's a y value. Now the notation for limits is to abbreviate it LIM, and below it we put as x goes to the x value that we want to look at where we're going to find our y value. Now in this particular graph, the thing that's interesting to me is the whole at -2. So we're going to find the limit as x goes to -2 of this function f of x. I don't know exactly what the function is, but I know what it looks like. So on my graph here, I want you to imagine that I've got these two guys walking down the sidewalk towards each other. And when x gets to -2, that's where we're looking to see what's happening. So they're walking down the sidewalk towards each other, and they get to -2, and there's a huge pothole in the sidewalk. It's huge. It's too big to walk over it, but they can lean over it and shake hands. Okay, so if they lean over that hole and they shake hands, at that spot, what y value would they be at?
-4.
They would be at -4. So the limit as x approaches -2 of this specific function is -4, even though the function doesn't exist at -4. So I use the example where I say I've got these two guys walking down the sidewalk. Can they meet up and shake hands? Because we're looking at what is happening approaching that y value from the left and approaching that y value from the right. But I don't care what's happening right at the point. Just to the left of it and just to the right of it, what y value does it appear I would land on? Does it make sense? Okay, let's look at another one. So I've got the same situation here, and if I want to look at the limit as x approaches 4 of this function, that's where the interesting thing is happening. So I've got somebody approaching from the left, somebody approaching from the right, and now I do have a gap in the sidewalk there. It's defined elsewhere though. In the first example, it wasn't defined at all. Now it's defined elsewhere. I don't care where it's defined. I care where they're going to shake hands. They're going to shake hands right there, right? They're going to lean over that hole. They can walk into it and fall down to the dot below, but we don't want them to do that. Break a leg, something. Right? So they're going to lean over and shake hands at what y value?
5.
So that limit equals 5. Even though the function evaluated at 4 is not 5, what would it be?
4.
It would be 4. It would be where we have the filled in dot. Okay, so these are two different things. It's not where's the function defined, it's what does it appear to be from the left and the right. Now, I don't always have to ask you about it in a place where something unusual is going on. I could just as easily ask you, what is the limit as x approaches 5 of this function? Well, coming from the left and the right towards 5, What y value do we get? 5. And what would the function be if I asked you to evaluate it at 5?
5.
So sometimes they match, but they don't have to. All right, on this one, I'm going to ask you to find the limit as x approaches 1. So I like to think of the horizontal as if it's the floor of a building. Okay, so the x-axis is the floor of a building. And I got this guy, I don't know how the heck he's getting from the bottom floor up to the first floor, but he's doing it somehow. He's riding a very interesting elevator that moves in a weird way. And this other guy is walking up the stairs. So when they both approach 1, they're in the same place vertically, but they're on different floors of the building, right? Can they shake hands? No. So a limit is what we're looking for is one finite y value that matches up from the left and the right. If it doesn't match, we say it does not exist. Now the function exists at 1. It's defined, right? That would be point B. But the limit does not exist. There's not a single finite y value that matches up from the left and the right. And for does not exist, we abbreviate DNE. All right, let's just try another one. Because again, they're not always tricky. What is the limit as x approaches 3 of this function? 0. It matches up and it exists there. Nothing tricky going on. All right, this graph we're going to look at several places. Got lots of interesting stuff going on. So we've got several different cases we've looked at. We can have a hole where the function just simply doesn't exist itself, but the limit does. So the limit as x approaches negative 3.5, looks like to me here, of this function, what would it be? It'd be about 0.5. Okay, so the function doesn't exist at that x value, but the limit does, because the y values match up. Okay, then if we look at negative 1, the limit as x approaches negative 1 of this function, is there a single finite y value that matches up? So we would say does not exist. That's called a jump discontinuity. You jump from one y value to another. The first one, if you happen to remember from college algebra, we call it a removable discontinuity, because there's things we can do to still be able to graph that without just saying, oh, the function doesn't exist at that point. And then we have the instance where the function is defined, the limit exists, but where the function is defined doesn't match the limit. So here, what would we say that limit is as x approaches 3? It's 1. And you'll be surprised how many people will tell me it's 2. Because it's ingrained in you guys to tell me what the function is evaluated at that spot. But that's not what we're looking at. We're looking at just to the left and the right of it. What is the y value? And then, of course, we have the easy ones. So what would it be? The limit as x approaches Oh, I don't know. Let's go with 5. About 2.5. Okay, and that one, the function exists there, the limit exists there, and they match up. So in this particular case, I'm given what the function is instead of the graph. The function is x squared minus 4 over x minus 2. Now what this function actually looks like is, let's see, something like that. And it's got a hole in it at x equals 2. Because when you look at the denominator here, when we determine domain, a denominator can't equal 0, right? And at x equals 2, we have a problem. And if I take you back to thinking about college algebra, what do we do to decide if that's an asymptote or a hole? Well, we would factor it. And we would say x minus 4 over x minus 2 is, well, the numerator's difference of squares. It's x plus 2 over x minus 2 over x minus 2. And those would simplify to 1. That makes it a hole versus an asymptote. When we can't remove it, that's why it's called a removable discontinuity. When we can't remove it, then it's an asymptote. Okay, but for this one, how do I figure out, if I don't have the graph, what the value is? Well, I can create a table. And we pick x values to the left and the right of the x value we're interested in. And from the left, I want to keep getting closer and closer and closer to 2. So 1.99, that's pretty close, but 1.999 is even closer. And 1.9999 is even closer. And then I want to come at it from the right. Really close would be 2.01, but closer, 2.001, even closer, 2.001. Now, your graphing calculator will do this work for you, okay? So let's look at that. Okay, so using the calculator, we got values of 3.99, 3.999, 3.9999. For this one, we got 4.0001. 4.001 and 4.01. So when we look, coming from the left, coming from the right, we see that we would meet up at 4.